Welcome to Spring Lib.
In this exercise, we have a fisherman whose boat travels with the speed v relative to the water, and the speed of the water itself is vw. The fisherman travels upstream for 2 kilometers until he drops his ice chest on the water, but he realizes that he dropped the ice chest 15 minutes after he dropped it. So he keeps traveling upstream for 15 more minutes. And then he realizes that he dropped and goes back downstream until he finds the ice chest, which is exactly at the point where the boat left off. And our goal is to find the speed of the water Vw in 2 different ways. In the first, we have to calculate everything in the Earth's reference frame. So let's start by noticing that in the Earth's reference frame, the speed of the boat is v prime equals v minus vw when the boat is upstream, and when it's downstream, the speed v prime is v plus vw. So notice that the total distance d that the boat travels upstream is 2 kilometers plus the distance the boat traveled during the 15 minutes before the fisherman realizes he dropped the ice chest. So this is the speed of the boat, v minus vw, times the time, which is 15 minutes. Okay, I'm just gonna convert this into the international system. So this is 2,000 meters. I'm gonna leave the units implicit, okay, because everything is in the international system, times, actually plus 900 times v minus vw. This is the distance, and the total time it takes for the fisherman to travel upstream. Actually, the total time it takes for the fisherman to travel downstream, td, is the distance that he traveled upstream, because the distance is the same, but divided by the speed of the boat when it's floating downstream. Okay, so let's save this. This is gonna be important. And what we need to do now is to go and work with the ice chest. Notice that the ice chest traveled 200 meters, sorry, 2,000 meters between the point where it was dropped and the point where the boat left off. And this is equal to the speed of the water times the time t. Okay, the time t between the point where the ice chest was dropped and the point when he reached the point where the boat left off. And this time t is the time it took for the boat to travel downstream plus the 15 minutes, or 900 seconds. So this is 2,000 meters is equal to vw, and now I'm going to substitute td, which is 2,000 plus 900 v minus vw divided by v plus vw plus 900. So 2,000 is equal to vw 2,000 plus 900 v minus vw plus v plus vw divided by vw V plus VW. So 2000 is equal to VW times 2000 plus 1800 times V divided by V plus VW. So 2000 times V plus VW is equal to 2000 times VW plus 1800 VW. So the 2000 VWs cancel out, and we have 2000 V equals 1800 VW. The V's cancel out, and we have 20 divided by 18, or 2000 divided by 1800, is equal to VW. So VW is 1.11 meters per second. And this is the answer in the Earth's reference frame. And now I have to move along to working with the water's reference frame. Notice that in the water reference frame, the ice chest doesn't move, so it keeps at rest during the time it takes for the boat to go upstream and then come back downstream. And since the boat has the same speed v relative to the water, the time it takes for the boat to go upstream is the same time that it takes for the boat to come upstream. And since we know that the time between the point where the fisherman dropped the ice chest and the time when he decides to return is 15 minutes, then the total time for the boat to go downstream then upstream to the point where the ice chest was dropped is 30 minutes. This is the total time, and this is equal to 1800 seconds. But notice that we know that during this time, relative to the Earth, the ice chest traveled a distance of 2 kilometers, so 2000 meters. And for that reason, we can simply calculate VW as the distance delta x divided by the total time t, capital T, and this is 2000 meters divided by 1800 seconds. And this is equal to 1.11 meters per second. And we obtain the same result.